we've talked about a lot of the basic math involved with unit conversions and collecting measurements, which are very important for chemistry. Now we're actually going to get into talking about the actual chemistry. So a question we have to ask ourselves first is, why study chemistry? Why should it be important? Well, you got to realize everything around you is made up of chemicals. That's chemistry. If we look at the elements as building blocks, those building blocks can be put together in different ways to form new building blocks, which can be put together to form even more building blocks. Right? We can keep combining until we get things in our life that make things go faster, provide entertainment, things that can bring harm to us, things that can protect us from that harm, things that prolong our life, things that can shorten our life. It's in the different types of food we eat. So salads versus really sweet things, those contain chemicals. Our sports entertainment, those involve chemicals. Whether you like basketball or badminton, those are made up of chemicals. Where you live, things you put in the places where you live. The pets you have, whether you like cats, dogs, or little rat type things. We're chemicals. Whether we're small or when we get older, it still involves chemicals. Our world overall, everything in it, involves chemicals. And it's not just our world, it's the entire universe involves chemicals in some way. Even the current processes going on in your brain as you're listening to this, as you're seeing these pictures, as you're trying to figure out what the heck is he talking about, these are all chemicals. It all involves chemistry. So it's very, very important to have a strong understanding of chemistry. So enough about that. Let's actually move on to talking about chemistry and how it relates to matter. All right, so from a molecular perspective, we can consider matter. Matter is going to be anything that has mass and takes up space. All right, you've probably heard that. So when we think about what makes up that matter, we can consider first something called the elements. All right, so these elements are going to be the building blocks that are going to be used to create the matter that we see. Now, when we think about the elements from a molecular perspective, we can treat those elements as something called atoms. So these atoms are going to be the smallest particle that we can get that still is going to retain the properties of the element. All right, so just a quick picture here. We've got these little spheres moving around. Those could represent individual atoms of an element. Atoms can be broken down into smaller and smaller particles, such as protons, neutrons, electrons, as well as we can take those and break them even further into fermions, bosons, quarks, leptons. But when we break it down from an atom, those smaller particles no longer retain the properties of the element. So the atom is the smallest thing we can break an element down into. Some elements actually exist as molecules. A molecule is just going to be one or more atoms combined together. If we look at this picture here, we can see we have two spheres attached together, moving around. Each sphere could represent one oxygen atom. Combined, we get the O2 molecule. That's still an element because both atoms are the same. They're the same element. Also with the molecule, though, we don't need to keep the same elements for each atom. So in this picture, we can see we have a brown atom and three blue atoms. So if the brown one was a nitrogen, the three blue ones were oxygens, we'd have an NO3 compound. Okay? And notice I use the word compound because when we combine more than one element together, it's no longer an element. But both pictures represent molecules. And we're going to get into that distinction between these two in the rest of our discussion. Let's consider the element iron, and let's consider the element oxygen. If I look at this picture here, I have an example where I have iron present. It's going to be present both in the material used to make the truck. It's going to be present in the material used to make that building. Oxygen, the element oxygen, is then going to be present in the air. So when we consider the iron that exists, that iron is going to be present in atoms. Okay, the oxygen is going to be present as molecules in the air. Now you might be able to make out on the truck something has happened on the top of that truck. And what's happened is we formed a compound. Now keep in mind a compound is going to be formed from two or more elements coming together. Compound we're interested in for this particular picture is something called iron oxide, or you may know it as rust. The rust you see on the pickup truck and the rust you see on the building is caused by that iron in those materials reacting with oxygen in the air, those O2 molecules, and combining together to form this Fe2O3, this iron oxide, or rust. Okay, it's going to form this combination where we have these different atoms of different elements combined together. So just keep in mind with these definitions for these components of matter. Elements are going to be the building blocks to make all of these different compounds. Elements can be in the form of atoms. Atoms are going to be the smallest form we can get an element to while still retaining the properties of that element. Some molecules exist where we have two atoms combined together, what's sometimes called diatomic molecules. But those both were examples of elements. We can also have compounds. Compounds are going to be formed from two or more different elements. And then something we'll talk about here later on is something called a mixture. A mixture is going to be a combination of elements or a combination of compounds, but they're not going to be combined together in a chemical reaction. They're still going to stay separate, but they're just going to be a mixture of the things. So here we have a mixture of those purple atoms we saw, the diatomic yellow molecules we saw, and the brown and blue compound molecules we saw. Combine them all together, we've got a mixture. But you notice each one of those is still retaining its own properties. They haven't actually physically combined together, we've just mixed them together. Now this is just a quick picture to show you some different perspectives to represent different types of compounds. So we've got oxygen, which has got two atoms of oxygen. Each atom is represented by that red sphere. We've got water, you've got the red oxygen, you've got two white hydrogen atoms combined together. We've got carbon dioxide. The central black atom is carbon, two surrounding ones are oxygen. And then we've got combinations of carbon, hydrogen, and oxygens in ethanol, ethylene glycol, and aspirin. This is just a different way of seeing how these things are connected. Now, one thing to note with these pictures that does cause some confusion, these are representations we've created. If we were to actually blow up an oxygen atom to look at it, it wouldn't be red, and water wouldn't be red and white. Okay, these colors we've used to just help us get a better picture of these things, but this isn't what they actually look like at the atomic level. Okay, just keep that in mind. For some reason it tends to cause confusions that everybody thinks all hydrogen atoms, they always look white. In fact, they have no color associated with them when we get down to the molecular level. Okay, let's continue on with our discussion. Now we're going to get into properties of matter. So we can talk in terms of physical properties of matter. Well, physical properties are going to be properties that don't involve changing the chemical composition of the matter. So let's look at some examples. We've got boiling point would be a physical property, freezing point, density. All those things don't change what the actual compound is. If I look at water, and I've got water going from liquid to a gas, that's boiling. Okay, the temperature at which that occurs is a boiling point. Why is that a physical property? Well, if you notice in the pictures, we've got water in the liquid form versus water in the gas form. We haven't changed what the compound is. We still have those compounds being a red atom and two white atoms. So we actually haven't changed the material. Now let's look at a physical change. Well, a physical change is going to be some change that doesn't involve a change in the chemical composition of the matter. In other words, boiling and melting. Once again, our picture. We haven't changed what the composition is. We've just changed it from liquid form to gas form. So changing from liquid form to gas form is a physical change. The temperature at which that occurs we'd call boiling point. That's a physical property. Let's look at another example of a physical change. If I take sugar and I dissolve that sugar, I'm going from solid sugar to what we call aqueous sugar or dissolved sugar. Now keep in mind, I'm not melting the sugar. Okay, I'm not going from solid to liquid, I'm going from solid to that little AQ, aqueous. Going from solid to dissolved. But if I changed what that sugar looks like, no, if I wanted the sugar back, all I'd have to do is boil off the water and I could get the compound back. So I haven't changed what the compound is, all I've done is surrounded that compound with water molecules to make it dissolve. Alright, let's look at another type of property of matter, and that's a chemical property. So, chemical properties are going to be properties that involve changing the chemical composition. This time around we're going to actually change what the material is. Examples of this are flammability, combustibility, reactivity. Let's look at an example of this. Going back to our iron example, if I start with an iron nail and I leave it exposed to the air, the iron atoms in that nail will react with oxygen, O2, in the atmosphere. When they combine, they form iron oxide, that rust. But you notice if we look at iron, it's a metal. It's got that metallic properties about it. It's shiny. Oxygen is a gas in the air. When we combine it to form iron oxide, we get this brownish solid material. We've actually changed what the materials are. A chemical change, then, is going to be a change in matter that involves changing the chemical composition. So corrosion, burning, those are chemical changes. Once again, iron going to iron oxide. That's a corrosion process. That's a chemical change. The fact that iron can corrode is a chemical property of iron. The process of going from iron to iron oxide is a chemical change. All right, let's look at another example of a chemical change. If we take propane gas and we burn it, we're going to form CO2 and water. So we're taking propane, which is C3H8, reacting with oxygen, O2, and we end up getting CO2 and water. We've changed the chemical composition of this material. Chemical property of propane then would be that it's combustible. We can burn it. Okay, so those are different types of properties of matters. And these pictures here go through some other different types of physical properties versus chemical properties. I'm not going to go through them all. You can pause the video for a second and take a look at these different types. But it's important that you get physical properties and chemical properties and physical changes and chemical changes understood, and you can discriminate between those. So let's get into dealing with some classifications of matter. What we're really going to discuss is how macroscopic properties can be predicted by molecular properties. Macroscopic properties are what we can physically see, what we deal with, whereas the molecular properties are what's going on at the atomic or molecular level. We're going to discuss these items in terms of the three major states of matter: gas, liquid, solid. All right, we're going to start with the solid state first. So if we want to look at macroscopic properties of a solid, we'd say that a solid has a fixed shape. We'd also say it has a fixed volume. If I take a cube and put it inside a flask, it doesn't assume the shape of a flask, and it doesn't fill up the flask entirely. Okay, it has a fixed shape and fixed volume. So why do we see these macroscopic properties? Well, let's look at the molecular properties. So with the molecular properties of a solid, we're going to have strong interactions between the molecules and the atoms. We're going to have very little space between those atoms and molecules when they're in the solid form. And those atoms and molecules are going to have very little movement. What does this mean? Well, because we have that strong interaction, those atoms and molecules are held tightly together and they're more fixed in place, which means we're going to have more of a fixed shape and a fixed volume. Because they have very little movement, they're not going to be able to move past each other as much, and they don't have enough kinetic energy to actually break apart from each other as easily. And so you'll end up not filling the shape of the container. They end up staying in their same set shape. Another thing to keep in mind, because we have very little movement in these strong interactions, when we go to pour the solid doesn't actually pour because those atoms and molecules can't flow past each other. So let's take a look at a liquid. If we look at the macroscopic properties of a liquid is going to have no fixed shape. Whatever container it's in, it's going to take the shape of that container. But the liquid is going to have a fixed volume. So let's look at the molecular properties. We're going to have medium interactions between the molecules and atoms. There's going to be little space between those atoms and molecules. And those atoms and molecules can move past each other. They're actually moving a little bit. So because we have the medium interaction, we still keep kind of a fixed volume. But because those molecules can move past each other, they can spread out. So we end up with no fixed shape. That's where we take the shape of the container. And as we pour this liquid out of the flask, that liquid would flow because those molecules or atoms can move past each other. And the last state we're going to look at is a gas. So if you look at the macroscopic properties, there's no fixed shape. It's going to take the shape of the container. And there's no fixed volume. The gas is going to completely fill whatever container it's in. So let's look at the molecular properties of a gas. There's going to be very weak interactions between the molecules and atoms. There's going to be lots of space between those molecules and atoms. And those molecules and atoms are going to have a lot of energy, and they're going to be moving fast. So because of these weak interactions, these molecules don't want to stay next to each other, so they're not going to hold together to form a fixed volume or a fixed shape. They're moving really fast, so they fill up the entire container. So when thinking about matter, thinking about these three basic physical states, solid, liquid, gas, also start thinking about in terms of not only the macroscopic properties we can see, but also what's happening at the atomic or molecular level. We need to start relating to that atomic molecular level because that's where the chemistry we're going to be talking about is occurring at.